My name is Langston Wilcox, and here is my presentation on Lab 1 charge tapes. I'm determining the excess charge on a piece of charged Scotch tape by analyzing charge tape samples, and I will use Newton's second law, Coulomb's law, to calculate the charge. We treat the charge as uniformly distributed and estimate the number of excess electrons using atomic dimensions. We're using three core principles: Newton's second law, F equals ma, which describes how motion changes with external forces; Coulomb's law, which explains the electric forces between charges; and the force of gravity, Fg equals mg, which helps us account for the weight of the tape in our calculations. For our lab preview, our experimental setup provided these results. The length of the tape was 0.21 meters, the mass was 0.21 grams, the distance between the tapes when one floated was about 0.27 meters, the gravitational force was negative 0.002 newtons, and the electric force was 0.002 newtons. While GlowScript calculated the charge on one piece of tape as 1.26 times 10 to the negative 8th, and the tape lost 7.88 times 10 to the 10th electrons during charging. For a lab setup, our system was 8-inch pieces of tape. Our surroundings were the lab room environment. We used GlowScript to calculate the tape's charge and model point charges. For our initial conditions, a neutral bottom piece of tape was pressed onto the table, and two upper tapes were pressed, ripped off, and used to determine the charges. For assumptions, we assumed that the U-tapes had equal charge and repelled each other. There was negligible air resistance, the U-tapes had evenly distributed charge along their length, and that the base tape modeled as a point charge. For our observed interactions, we had that the U-tape was attracted to the hand, indicating an opposite charge. Neutral charges showed little attraction to the U-tapes, and a strong repulsive force confirmed the U-tapes had like charges.
It's not working. There you go. It's getting stuck on the side. It's being taped down.
Yeah, I can.
Okay. Yep, go. You get that last bit?
Oh, what? Oh, wait. You see this? Wait. You see this? Are we close to the checkpoint? I think so. Yeah. Are we close to the checkpoint? I think so.
I'll put a pause.
Here are a few videos of our attempts to get the tape to float. Here's my code. As you can see, it calculates the amount of singular tape charge, electrons lost, atoms per electron on the table, the gravitational force, and the electric force. And here's my diagram that shows the tapes were closed before one began to float. The computational model treats the tape as a point charge with only electric and gravitational forces, whereas the experimental model accounts for the tape's distributed charge and external forces and distributes the forces evenly. However, both models showed a positive electric force and a negative gravitational force in the y direction. Some potential sources of error include air resistance, which might have slightly impacted the results, calculation or GlowScript errors, which may have caused discrepancies, and charge transfer from handling the tape could have neutralized the charge, affecting the measurements. These are all factors which may have forced the two tapes to be so close in order for one to float. For the what-if question, the signs of the charges would flip and the direction of the electric field would reverse. However, the attractions and repulsions between objects would remain the same since all charges would flip uniformly. For the why question, handling the tapes carefully is crucial. If you touch the tapes, charge transfer can occur, neutralizing their charge and skewing results. By minimizing contact, we maintain the tape's charge integrity and ensure reliable results. In conclusion, this experiment successfully demonstrates how the excess charge on Scotch tape can be calculated using Newton's second law and Coulomb's law. By assuming uniform charge distribution and using a computational model, we were able to estimate the charge of the tape and understand the interaction between charged objects. While potential sources of error exist, such as charge transfer and air resistance, the results showed that handling the charge tapes carefully is crucial to avoid neutralizing the charge. However, This experiment provides valuable insights into the behavior of charged objects in a controlled environment.